All right. So Miles, you can go ahead. And today we'll have Miles and Salman to give a very quick introduction on the virtual environment needed for completing the programming assignment. Miles, you can go ahead.
All right. Thank you, Dr. Yao. Hi, I'm one of the TAs for the class, like Dr. Yao noted, and to start off with this lab, you need to download VirtualBox, and I'm running VirtualBox from my Linux-based system, but VirtualBox has various instructions for all the different operating systems available. And I won't walk through specific instructions since VirtualBox does the job of instructing you how to install it for your system itself. And after you download VirtualBox, you also need to download the lab for this, and you can find it at this link here. And we specify you should use the Ubuntu 16 seed. However, you can use the Ubuntu 12. It would just be easier for us and everyone if everyone in the class used the Ubuntu 16 version. And it doesn't matter which source you download it from. I believe all of these are the same zip file, just hosted in various locations. And once you download that and unzip it, you have to import it into your VirtualBox. And I'll quickly walk through that myself. And also, this is following along the actual URL showing you how to set up the seed virtual environment from the same URL from Seed Labs. And first off, you should go to new VirtualBox. Since this will be a new virtual machine, you can name it whichever you want or whichever name you want. And you should specify Ubuntu 32. And it's recommended from the lab to go increase the RAM, but you don't need to. And specifically here, you have to look for a specific VMDK file. And this may differ depending on where you downloaded the files and unzip the files. But once you get to that folder, you should go to the base VMDK without any numerics in it. Well, unfortunately, sorry about that. I've already pre-run this myself, so we will go ahead and skip that step. And once you have it, it'll pop up with a virtual machine like this. And from here, I'll follow along a couple of steps, but a couple of these are also my preference steps as well. What you should do so many of the steps here you can set up to help aid you in running this lab, where normally I like to share the clipboard or share drag and drop options from my host machine to virtual machine. And you can select them from settings, general, shared clipboard, and drag and drop. And you can also mount a folder from your host machine, which is whatever operating system you're running, into the virtual machine from here. And this will aid you if you want to save files on the virtual machine and then access them and submit them or take pictures of them or anything in between. And for that to happen, you have to install the guest editions for VirtualBox for that virtual machine. and I can quickly go through it. And it should come with any VirtualBox installation. And I believe it was, or it may be asked later on, but I'm running this lab on VirtualBox 6.1, and feel free to use the latest version of VirtualBox itself. And while it's still booting up, if you click this disk icon down in the lower right, you can select the VBox guest editions. And if you wait a couple of seconds, it'll pop up with a menu on the virtual machine asking if you want to run it or not. And I'll go ahead and just push cancel for now to make things go faster. And something that I'm doing on and off currently is I'm saving the machine state and saving different snapshots, or you can think of them as checkpoints of the virtual machine, where they allow you to roll back and capture the exact, capture whatever you were doing in that exact instance of the virtual machine. So any active programs, as you can see, several active programs are already here and showing. And feel free to do that as much as you like. So I already have the VirtualBox running, and you can see, since the screen is easily enlarged, I have the guest editions running. And after that, you should be able to quickly, or after all of that setup, you can quickly go through the lab and start doing the tasks itself. And I'll start off by going through, and actually I'm just following along the lab instructions as we go. And as you can see off screen, I just copied one of the setup instructions to turn off the address space randomization. If I click to paste, it will automatically paste whatever I copied from my host machine to here. And I'll do that as well for the stack guard protection scheme. And as you can see, it pasted there, which oh, well, forgive that, that's for an example program. And before I continue any further, since this lab does go over compiling and executing C files, I would highly recommend for you to, or any of you feel free to, but I would highly recommend for you to look into a program called a GDB. GDB allows you to essentially decompile and walk through the execution of a C file, a compiled C program. And I already have a custom wrapper installed here, but since GDB is a little, at least it's hard for me to understand and see what's going on in GDB, and GDB is already installed on the virtual machine, I'd recommend for each and every one of you to download this .gdb init file and just paste it into whatever directory you're planning on running the lab. And it gives you a easy to use, friendly, automatic layout for the execution of the code. And I believe I can post the link on Piazza later. And I can walk through a little bit more of the lab where where I have the call shellcode program already on the Sublime text editor. And again, I would recommend using this since I don't know how many of you know VI or Vim, but this is always a quick and easy editor. And from here, I believe the first line that you can copy and run is actually compiling the call shell code. And if we do a quick run through of the shell code, which is call shell code, we can see that just without adding any breakpoints, which are execution spots where the GDB will pause to let you look at it, GDB will already show you a lot of these variables without adding any kind of extra markers onto the compilation. And I believe this should be a good start for continuing and running the lab. Do you have any extra, oh, sorry, what?
This is excellent. Feel free to drop by TA hours of our office hours of TAs. So this is excellent. Thank you so much, Miles. Anything to add, Miles?
I was just gonna ask Salman if he had any tips or tricks for this lab.
Yeah, okay, Salman also has something to share
Yeah.
and so Miles, if you can stop sharing. Yeah.
So basically Miles has covered most of it, but I just want to remind, so when I tried to reproduce the exploit, some of the key things that I made like mistake or I didn't notice is make sure that the address space randomization is turned off, because you might see some like permission related issue where you think it's already been set, but it's not set. So if that's the case, you will never going to reproduce the exploit. So make sure the randomization is turned off before you starting the exploit. At some point you need to turn it on, but when you get to that point, you will understand why this is happening. So make sure you turn off the randomization before starting the exploit. Then Miles also showed you some of the key things about GDB, like nice interface, but three key things you need. Like you need to find out the address, like basically the starting and ending address of the buffer. So you can look at the address by issuing the command X and the buffer, that's the buffer name. That will give you the starting address of the buffer. Then you can just add some like length. For example, in your stack code, you have the buffer size about 24. So if you give X buffer plus 23, that will give you the end address of the buffer. So you need that. Then you need the base pointer, like as I mentioned here. The base pointer starts just after the buffer. So you need to know that base pointer, because you need the base pointer to know to get the address of the return address or the content of the return address. To know the like content of the base pointer or the address of the base pointer, you need to issue X, then this $, then EBP. So since it is 32-bit system, the register start with E. But if it is 64, then it starts with R. But since we are suggesting you to use the 32-bit, so it will be always start with E. So to get the address of the base pointer, you need to issue the command X $ABP. Now if you need to look for the return address, you need to issue the command X $ABP plus 4. So I should have like copied the output here. That will make more sense. But when you issue this command, the left side will have the address, then colon, then the right side will have the content. So you can see which address has which content. So you need these three things. Then you need to store the shellcode in the stack at some point. And like for example here, I stored the shellcode some point in here. Then you need to override the content, like so this X $ABP plus 4 will give you the address of this slot in the stack. So you know the address. Now you need to override the content of this address by pointing to this shellcode. So this is the exact way. And you can like approximate the, not approximate, you can just calculate the address where you are going to store the shellcode. So once you have that address, you just need to put that address in appropriate place in your buffer to override this return address. Now, this is the exact precise way, but you can also point out this return address any of these, like after this return address and before this shellcode, since all of them are by default put by the end of instruction. If you follow the exploit code, like the sample exploit code, it's already pre-filled with this NOP instructions. So if your return address is pointing to here, it will essentially go to the shellcode. So that the imprecise way, like it's little flexible, give you little flexibility, but you can precisely override with the shellcode. So that's how we override it. And finally, like don't type the shellcode because it is very easy to make mistakes in the shellcode if you are going to type it. And if you make mistake typing it, you will not get the shell. So that's some of the quick tips I wanted to share.
All right, thank you so much, Salman. And if you could send me the slides, I'll incorporate in mine when I release it. All right, this is excellent. Thank you so much. And hopefully this will give you guys enough information just to overcome the mental barrier to get this project started, programming assignment started. We didn't do this before, but I feel like during COVID, we didn't see people in person, and this will help you just to warm up to it quickly. All right, thank you so much, Miles and Salman. Appreciate it.
Yeah, sure.
All right. I'll go ahead and start the discussion. We want to continue the discussion of buffer overflow, and today we want to just to see a couple more different flavors of software vulnerabilities and integer overflow, data-oriented attacks, and where code reuse attacks. And so, as you all know, if you know the attack, it's easier to defend it. So part of it, this exercise is for you to get familiar with all kinds of different flavors of vulnerabilities. A little bit of recap, control flow means order of execution. We look at assembly code, machine instructions, and you're gonna see more of it in the programming assignment. Attacker is able to calculate layout, like Salman said. If you turn on ASLR, then that's gonna be very difficult. And so for this exercise, ASLR is off. A left one's paper is extremely important to read it. If you haven't started reading it, read it back and forth, back and forth. Last time we talked about attacker, how to increase the chance of success by doing a no-op sled, where you can point to the new return address somewhere in no-op and then it slide into shellcode. input validation, and we're going to talk about input validation throughout the course. And so this is just to take a step back, what's going on in buffer overflow. And on the left side, the green colored flow, this is a normal, well-formed inputs. The victim program takes it and then run it. Everything expects it. But then the attacker would abuse the vulnerabilities in the victim program injected with ill-formed inputs. And then that will cause the control flow to be altered in a way that would be beneficial for the attacker, or at least cause the victim program to crash or to hang. And so a lot of the starting issue is the ill-formed inputs. And so if you're able, you being the developer, you can stop ill-formed inputs by just to validate inputs, bounds checking, sanity checking, remove different tags and make sure it's not too big. It'll save a lot of people a lot of trouble. But however, as we will see, it's just not always possible, because sometimes it's just so subtle. You just don't know that this will actually impact control flow. And so, but if you can remember to validate inputs, always do. And then the inputs may not be coming in, it's just all kinds of inputs. And so really the key is it possible for you to realize that you're actually taking inputs from untrusted sources. And so talking about prevention, of course, a lot of the legacy functions are just so broken and it's not recommended to use it. There are safer alternatives. And so remember to use that. And there are here and there, just on the web, different people have different places to talk about safe functions. And so it's sort of a best practices. You have to you have to find them, okay? And so for example, some of the string copy operations, they don't terminate with null, and that could create issues. Strings should end with null. Defense, other more systematic defenses, non-executable stack, which is widely implemented. We'll talk a little bit more. Canaries, we'll give some more examples, and ASLR and so on. Boundary checking, developers should do it. A compiler should also do it. Compilers will save a lot of trouble. And so there are safer languages that restrict the way how you allocate memories. C, you just so much freedom in terms of allocating memory and the function pointers. You don't see a lot of those in Java. It's a lot more restricted, make it safer. And of course, last time we focused on stack buffer overflow. Today we want to see more of a similar type of problem, but not necessarily on stack, not necessarily sort of a overflow. But in general, what attacker want to do is to redirect the legitimate control flow to fit attackers' needs. And so the normal control flow may have call and jump and a return, and those are the critical joints where attacker can exert influence. And if it's continuous instruction, one by one, and then they couldn't do much to change it. But whenever there's the opportunity, whenever they say, the function says, call this subroutine, and this is, use this function pointer, call whichever function pointed to by this code pointer, and this is where they comes in. If they can change the code pointer, the address pointed by the code pointer, and the code pointer can point it to somewhere else. And so in general, all these critical places are places where defense need to focus And of course, it doesn't need to be stack. It could be heap. How is it? Heap has no return address. And last time we said that stack is for managing function calls. Function calls, subroutine calls need to return back to the caller function, and that's where the return address, right? So, but the heap does not manage subroutine calls, and so has no return address. So how is this useful? It turns out Heap has uninitialized data structures and the dynamic data structure. And you can have function pointers, linked list. You can have a linked list of function pointers. You can add, in C, you can allocate the struct. It's some sort of structure. It's sort of like an object that it can have local field. It can have function pointer to process the local field. And then whenever there's this code pointer, you have to be on high alert, okay? Because this is where attacker may take advantage of. If they override the function pointer and then point it to attack code as this figure illustrate, then you're gonna have problem. And so here is a simple example, a C example, and that I stole from the book by Stalling. So not sure how familiar you are with C code, but this is relatively simple. So what it does, it has a main function. The main function does a whole bunch of things, but outside it defines a structure. It's a struct called chunk. Chunk has a local character array, and also has a function that calls a function to process a character array with the input of a character pointer. So this is a function pointer, and then it has another function defined. Okay, I define another function. And so in the main function starts with allocating a chunk, okay? And then, because chunk is defined to have a character array and a function pointer, so therefore at this time, you will have the function pointer called process appearing on the heap, okay? And so it's pointing to whichever it was defined. But however, you see at the in the main body of the main function, it says gets. Whenever there's gets, you have to be on high alert. Okay, gets input from standard input from user, and then in this case, there's no bounce checking, and based on the allocation of the heap, which we'll now show today, but this input, if not properly checked, will be able to overflood and overwrite the function pointer and causing problems. And then you can have similar type of shell type of code that redirect the new function pointer to the shell code. So it's very similar. It's very similar, and a lot of time that you have external input that reach the elements that can change the control flow. So the key goal is to prevent attackers from altering the control flow. And so this shouldn't be really difficult because what the program is supposed to do, we know the source code or the byte code, you should know, or the executables, and so you should be able to know what the program does, right? If the programs all of a sudden start to execute a shell, but then you couldn't find anything like that written in the code, then you know there's something wrong. So that's the basic idea of control flow integrity defense. And so it's called a CFI. This is a defense approach. Very, very popular. The concept is very simple. You just have you observe the program's execution and the runtime. But then before that, you already mapped, you have a map based on the control flow graph. You look at the code, you look at the structure of the program, you know how it's supposed to transition, you know, the control transfer, who calls what at what time. And so then you just compare. You see, okay, the runtime, or I'm seeing a new shell code execution from you know, this execution full, and then you look at what it's supposed to do, that it doesn't match. So very basic, very simple concept. There are some difficulties when you implement it because you know, for large programs, it's hard to predict. But then that's essentially what CFI does. CFI is so popular, Google decided to implement it in Android kernel security, and this was the 2018 news. So you have, and then there's different flavors of CFI. You can have a coarse grain, the fine grain, and depends on the overhead and how well you approximate the expected behavior of program. Sometimes you don't know. For example, if the code says, okay, I'm going to execute this function, but then the function depends on the dynamic input. So you don't exactly know which function is to be executed. You just have to, you know, approximate it. So CFI is very, you know, has a lot of industry attention from both software and hardware side. Intel decided to work on hardware implementation of control flow integrity. You just have some ability to encode the correct transfer in some registers and then enforce it at the runtime with this hardware support, which is a lot faster. And what is it called? The concept is called shadow stack, but essentially it's the same thing. You have ability to record the correct transfer, the target address, and then compare it at the runtime. Control flow enforcement technology, CFET, started, I think, in 2016 and was implemented in Windows 10, I believe. So it's very fascinating. And the possible class project idea is just to understand hardware CFI and then see if you can evaluate some aspect of CFI. So next Thursday, we're very excited to have Salman come back again and talk a little bit more about CFI. His dissertation research is on ASLR measurement. And so he will talk a little bit more about the intricacy, the details of how CFI works, and then the difficulties in ASLR and so on. So buffer overflow, and whenever you have a buffer, it can be overwritten and then override return address, override function pointers. But there's also other issues that does not necessarily involve a buffer. One of it is called use after free. Use after free is related to pointers. Pointers that points to functions or point to data field. And so it's not overflow type, but I want to talk about it. You see that there's a lot of similarities. And so this is, we heard about this before when Salman gave the Internet Explorer 8 demo. That exploit leverages a use after free vulnerabilities in IE8. That end up enabling the attacker to take full control of the machine, which is, if you think about it, is very dangerous because you have a browser, which is just an application in the system, but then the vulnerability bleeds out to the whole system, enabling the attacker control the whole computer. Use after free here is an example. If you look at the lower right. So you have some buffer 1, buffer 2, you do some operation, and here there's some free, okay, free operation. The buffer are free, but then it gets used again at line 34. In the printf, it basically says, okay, what's inside the buffer? And so if buffer was pointing to like password, social security number, credit cards, private keys, and then now printf may leak information. And then you also have a copy. You copy things over, and this is also not very good because it depends on what's inside the buffer. You may copy attacker's input into the memory. So a little bit closer, another just diagram, right? So you have a free block you allocate with something, a pointer, and then you process the printer, they end up may store some information. It could be insensitive. In that case, you don't worry too much, but could be also be sensitive. And then at some point you said free. When you say free, the memory content is still there. It's just temporarily marked as this space being available, but then there's no erase operation, okay? The memory takes a lazy approach. They don't actively set it to no. And so far so good. If nobody use this again, if this point PTR, this pointer is never referenced again, then it's okay. But however, if this is used again, if someone says printf or someone access this, they will be able to access the memory content where this pointer was pointing to. That could leak information, right? So how is this? I mean, it looks like such a small problem. But then it's just bad. It's bad because the developers forgot this was free again, or because it was defined twice, right? So you forget, you developers end up using the same name for variable, and then there's clashes, and so all kind of situation that may lead to use after free. And so it also called the dangling pointers, and so it has to be set to null explicitly by the developer, or you have some sort of a garbage collector, you have some sort of automatic memory management that clean up all the dangling pointers. And so but be aware, okay? Be aware whenever you say free something, it never gets totally freed. And so set it to now. I forgot the instruction that set the pointers to now, but set it to now explicitly. Integer overflow. How bad can integer be? Like they don't even change control flow. There's no return address of pointer, function pointer. So why am I worrying about integer overflow? It can actually literally kill people. Back in the 80s, there was this very popular chemotherapy, therapy machine, and nowadays it's a lot of the cancer was treated through chemo, not radiation. But it was popular back in the 80s, and one of the machine called Serax 25 end up caused several fatalities in North America, between US and Canada. Several people died because the machine over released radiations on the patients, and the nurses saw that the machine was not releasing any radiation, and then keep heating, increase the dose. And then the root cause, there are several issues. One is, well, part of it is that at some point the code was written in assembly level, very hard to debug. And then, but then there's some change in the design. There used to be a hardware interlock that prevent this kind of thing from happening, prevent the metal shield from going away. The metal shield is used to measure the amount of radiation, and at the time of incidence, the shield was away, and so the radiation just never gets measured, and part of it, there's also integer overflow causing the software to bypass safety check. Really, really very, very sad. And the integer overflow is just bad because there's finite size of a register, how many bits you can hold. And so if the integer is too big, for signed integer, then you can also have this wraparound problem. The sign gets lost, the numbers has a different sign. And so it's just unpredictable behavior, undefined behavior can get exploited. How is this gets exploited? Well, what if the integer is used to control a loop? How many iterations it goes into a loop. In that case, that you could end up having either too many iterations or too few iterations, and that end up changing the control flow. So something that has to be prevented, and one of the prevention is to use built-in functions that automatically check for integer overflow. Another one is, of course, always validate and sanity check. If you take some integer, make sure it's within a bound that you're expecting, and so that both sides, one is the developer side, the other is the system size, and we need both sides to work very hard to make sure that there's no unexpected behaviors, no surprises. Integer flow is, you can see that as a type of data-oriented vulnerabilities. Data-oriented vulnerability that impacts the data variables. It does not necessarily directly change control flow. Stack buffer overflow is a control-oriented attack. It changed return address. The heap overflow example that we showed with function pointer is also control-oriented. But data flow is also vulnerable. Data flow function needs data, right, to make decisions. And so whenever the data is tampered with, then the decision is tampered with. So here is an example. This is for authenticating a user, okay? If the user's password matches, pass, otherwise rejected. And so what happened is that there is a very, very important data variable called authenticated. It was set to 0, only set to 1 when the password matches. But however, the code has a problem. It takes external input, okay? And then this is, I believe this is either made up example or an example appeared in very early version of some OpenSSL client. So it's take packet, whenever you read packet, you get something from standard input network, you have to be extremely careful, because the way that this, on the stack, this local variable is allocated, as we've shown, you allocate arguments, return address, local variables. and then you proceed with allocating this, whatever input that you read, things may overflow and override the variable, And the attacker may able to control this buffer that gets written into the memory, and if they are careful, you can set it to 1, then the attacker gets admitted to the system without knowing the password. So it's really bad. The data variables can cause serious damages, and so of course some datas are okay. Some data variables are okay if it's just doing some local addition and not used to make any control decisions. But then if the data is used to make control decisions like before, right? So authenticated or not authenticated, that value impact how the program is executed. Similarly, if you have, like other if statements, the predicates, the variable that goes into the predicates of the if decision impact the control decision. If you have a variable that controls the loop, the bound of the loop, how many iterations that control that impact the control decision. So all these values are very important. They look benign, but they're very important. And if the stars are aligned, they could be overwritten, could be controlled, like we shown in the previous slide. And so I mean, it's just a different flavors. As you can see, we show you different flavors of how the vulnerability, and then we're gonna have a little bit of pattern, and then you can almost see some patterns here. This is a very different flavor. Back in 20, I forgot when this came out, maybe 6 years ago. Shell shock vulnerability is very simple. It's essentially, so you see this environment, right? So in the shell you can change the environment variables, right? Environment variables, and you essentially the code that implement this command does not do any sanity check before evaluating the parameters, the string that comes with it, and so end up enabling the attacker to execute arbitrary commands. And so basically attacker would set up a command that may superficially look like, oh, I want to change my environment, I want to set a certain path. But then part of it is not just, directory and so on, it's an actual command, okay? And then this program will just blindly execute the input. And so that caused a problem. So again, you see the pattern here. You take untrusted inputs and you don't do any sanity check, and then you execute it, where you interpret it in a way that impacts your actual control flow. So I mean, the simple fix is just to sanitize. If there are echo, if you don't expect the echo to appear in the environmental variable, if you only expect some path, like directory type of string, then say it, enforce it. But for overflow defenses, we've already touched some of it. Boundary checkings, validate inputs, use tools. Use tools to scan your code, use built-in safe functions. And it's almost that you don't have to worry about all of them now, but then you should remember in the future, whenever you write C code, you should say, wait a minute, am I using save function? Am I doing control, boundary check? Am I using tools? So always remember the risk. The risk is always there. There's also system architectural fixed defenses, stack canaries, no execution bit. This prevent stack from being executed. So we're gonna go through some of it. One of it is a stack canary. The concept is very simple. It's very smart. You put a secret, and this is very important. You have to make a secret. If it's a very well known, like 1, 2, 3, 4, then anyone can rewrite the canary with 1, 2, 3, 4. So it has to be a secret. And then, it keeps changing. Like if you do full has its secret, bar has its own secret. So the OS will sign the canary value and then put it right above the return address. And the assumption is, of course, is that the attacker cannot know the value. And if you have a vulnerability, the buffer gets overflown, and then the canary value is also gets rewritten. And so instead of being the actual secret value, you have whatever, some other junk. And then the chance of attacker accidentally guess the canary value is very low. And if you think, 32-bit or 64 bits, it's very hard to guess. So again, assuming the attacker don't know how canary value is generated and cannot find it. And so this would work is you just indicate that there's something wrong has occurred, and then you stop the execution, right? So, and of course, the disruption is still there. But then at least you're not executing attacker code. No execution or W XOR R, or also called Data Execution Prevention by Microsoft. The concept is very simple. The memory, the part, it can either be rewritten, like if you see a data region, stack region, it can be rewritten, but then it cannot be executed. Like a data region cannot be executed, a stack cannot be executed. And who is enforcing it? Well, you need some memory management unit, the hardware support to be able to enforce it. Or the software, there's this region is allocated to stack. I'm not gonna allow execution operation. Some complication, you may in some situation have code that are dynamic in the way that you may have to allocate code. A lot of the JavaScript is very dynamic. Once it gets written, you don't know exactly is it code or is it get executed. So there are some limitations. For certain type of language, it may work. For other type, it may not work. But in general, you know more. If you know more about your expected behavior, then you can put some restrictions around it. ASLR have different flavors. And so this a big map just shows that there's like random stack offset. Random stack offset where you don't begin by always starts at 0 or as expected position in your virtual memory. You like off a little bit. You have a random starting point. And this is, of course, illustrating the basic fine-grained ASLR, because you see the stack is still consecutive, right? So this is still consecutive. And here is also still consecutive. It's just a starting point that gets randomized. And so this is called a coarse-grained ASLR. And there's also other flavors. Other flavors, function level, block level, and then the most fine-grained. Well, instruction level, and then you can also do register level randomization. Those are much more fine-grained. And of course, it's more costly. You know, you spend more time finding where everything is. So ASLR is useful not just for stack overflow, but also in general code reuse attack. Code reuse attack will not be very effective when you have properly implemented ASLR. And so it's complicated because there are different flavors of code reuse and then different flavors of ASLR. But in general, code reuse is very different from what we talked about. We show you the example of injecting shellcode. Shellcode may or may not appear in the original victim program, right? The instruction to start bin /bin/h. So it may look foreign, alien. It's an alien code. Attacker injected into the victim memory space. And in theory, it should be easy to be detected. If you just look for /bin/sh, or something like of that flavor. You know, you see execution. So it's not good from attacker's perspective because it's very easy, relatively easy to detect. Code reuse attack is a more sophisticated attack. It reuse and reorganize the existing instructions in the process of a victim's process. And so the victim may have maybe a big program, may use some library code, and so has a lot of instructions already in the memory space, in the text region. Why not just pick and choose of the instructions that the attacker needs? And so it's sort of like a jump around. It can jump around because it utilizes return address and or jump, and whenever there is a control transfer, attacker may be able to take advantage and then direct the control flow somewhere else. So code reuse attack is bad. There's a, we'll describe it more, and there's a concept called gadgets. It means just a short consecutive instruction sequences. And so they piece them together. The good thing is that the instruction level randomization is extremely effective against gadgets, breaking up gadgets, breaking up code reuse attacks. Because it's just, if you randomize every instruction, the instructions are no longer consecutive. And it used to be, you know, you do 1, 2, 3, 4. Now you have to find them. You have to find them. And if you don't know where everything is, then the consecutive instructions just look random. And so, I mean, it's just all over the place. So code reuse is gonna be difficult. But you may know how can this be possible if the instructions are no longer following the correct order? Then, you know, how can normal programs get executed? How can normal programs work? So that's a very good question, and let's take a look. In instruction level ASR, the short story is that there is a secret mapping that tells the legitimate program where everything is. You can put it away, but as long as you keep track of the new address, and then you can still locate it, right? So before, without ASLR, you have this kind of consecutive memory space, right? And then with the ASL instruction level ASLR, you look at the addresses just look so random. But then you have this fall through map or whatever mapping you call it that tells you if you want to find address, the real location is where. Okay, and so you basically will still be able to chain them together, right? So that's the basic idea. And of course, it's gonna be expensive, but turns out in our experiment, Salman hopefully will cover some of it. It's not that bad. It's adds a little bit of overhead. It is certainly tolerable if you have a highly critical operation. Yeah, it may not be useful for everybody, right? But it's a trade-off. My other research, we also look at the code patterns. You know, what pattern? So is there a way that you can estimate how risky a program is, especially legacy programs, and you want to change them, you want to do something, but then you have to know, you know, how risky a program is, and the programs basically you assume that it can be very risky. So can we measure it? Can we approximate it? And you look for patterns, and all the issues that we look at has similar flavors. You take external inputs, you don't do boundary checking, and then the input can reach sensitive data elements, pointers, address, and so on. If the input is just standalone, nobody use it on anything, or it's the way that it's allocated is cannot reach any useful information, that's probably is fine. And then the sensitive elements obviously can impact data flow and control flow. And then this would just connect attacker with your sensitive data flow and control flow, right? So in this case, then you know this is a high risk pattern. So you know, just understand your code a bit more, and then you'll be able to detect them prevention. So Salman will talk a little bit more about this. And in general, that you'll see, and this is, you know, ASLR, it also represents this paradoxical aspect of cybersecurity. On one hand, you want to have normal programs to execute, but then you also prevent hackers from abusing the code. So you randomize the location of the instructions, but then on one hand, you also want to make things faster, right? So when you sell computers, the regular people would not first ask, how secure is this against a data-oriented attack or control-oriented attack? They will ask, how fast am I gonna, you know, how good it is so when I watch movie on this computer or play video games. And so it's a trade-off. It's a lot of times that it's, you have to keep a balance. And it all depends on how risky your operation is. Before we end, I want to talk a little bit about buffer overread. And so far we talked about its override, right? Override pointers, override return address, override, you know, flags. Use after free can be overread issue, because when you free the pointer and then you access again, you can do printf and then you access, and that's read. The most famous, of course, buffer overread is called Heartbleed. In a lot of times in recent years, every vulnerability has a name and also a logo. Heartbleed was discovered, was reported several years ago in TLS, and we talked about TLS. It's extremely important for network security, and in TLS library, people find that, I think in 2014 people find it, but the vulnerability existed for at least 2 years. Enable hackers to be able to read the memory content of a server. And so what happened is that there's this, in TLS, there's a simple beacon, like heartbeat type of operation just to make sure that things are up and running. So the client has the option of saying, server, are you still there? If so, reply something. And then this reply has 6 characters. Suppose it's potato, 6 characters. You just reply potato, give me 6 characters. However, the problem is that the 6th character is specified by the client. And so if you have a malicious client and they say, server, are you there? If so, reply hat. But the hat has 500 characters, which is obviously wrong. But then the server will blindly trust this value, 500, and then therefore reply, religiously read the memory and then find out 500 characters and send it back to the client. And then where those 500 characters about? Well, it's whatever comes after hat. So there could be password and secret key and then so on and so forth. And because you don't know what's being stored in the memory, it could be useful, it could be junk. But then if you are lucky, it could be private keys of the server, right? And so you don't want our client attacker to unnecessarily get a peek of what's inside the memory. The memory stores a lot of information that are not meant to be shared by the client. And so those are the 3 lines that are the culprit. So you have payload, and then you have a memory copy. Memory copy, the payload here is a variable that specifies the length to be copied from the memory and then shared with the client. And except the problem is that payload is defined by the sender, the client, okay? And so you have untrusted data, in this case it's payload, that impact your data operation, right? And in the control and data operation, how much you read. So the code was there, and then this is really, I remember the report says the developer, they're very experienced, but then made a mistake, completely like inadvertent mistake. And all these developers, a lot of those library developers are unpaid and like volunteers, and probably they're paid very, very little, I would think. So this is a before. Before you have read, and so N2S is apparently get information from the client, and so this payload gets populated. The payload value gets populated, and then afterwards in this fixed version, there's a sanity check, and there's a check that make sure this is not exceeding the maximum length, okay? And hopefully the maximum length is small enough so that you don't reveal unnecessary information. And so you see, this is just the different kinds of, and there's, the blue line, the green lines are new code. So that's it for today. Just hopefully you get a lot of information. You see different flavors of software vulnerabilities, and then the root cause is, of course, the external inputs. Okay. And next class, we want to see a little bit more about return to libc. We didn't have time to do it. Return to libc, we'll say a little bit more about it. And then other software vulnerability issues. Okay, that's it for today. Thank you so much. Have a nice weekend.